Yeah, Carlotta, thank you very much for the introduction and for the poll. Very interesting to see who is participating. Good afternoon or good morning, ladies and gentlemen, to everybody. I'm happy to see so many people attending this webinar. I will present together with my colleague from Fraunhofer IKTS, Uwe Scheithauer, who is one of our leading customers, and as Carlotta was also already saying, the leading institute in ceramic processing. But let me also introduce you a little bit to Lithoz. What are we here? You see our team last autumn. So we are about 70 plus people here in Austria and in the United States. So we have a location in Troy, New York State. And we are a solution provider for additive manufacturing of ceramics. So we are offering printers, materials, software, and as well customized solution and trying to support our customers and partner in every aspect of the process chain. Currently, we have about 70 machines. It's 70 to nearly, it will be 80 soon, machines worldwide. And one of our good things is what we see is that 25% of our customer have more than one machine, which shows us that our approach in supporting the customer in developing their application works out very well. So this 25% is actually a huge number for additive manufacturing, and especially for such an early technology. And hopefully, we can also support you through this in your applications. So, slide, sorry. Yeah, this was just very brief introduction what we do. I want to introduce you as well a little bit to the ceramic materials to give you an overview what are ceramics and why are they used. Basically, ceramics are basically a very old material, an old tool material. So it has been used for 30,000 years now. As you can see, there's been done some art, and also clay and pottery have been made in these early days. And basically, and that's we will see it later when we come to the medical applications, that ceramic is basically a natural material, which also is in the nature as ceramics. And in contrast to metal, which is usually also in a ceramic way in the nature, so it's usually an ore, and then that's why the body is also very likely to accept ceramics much better than metals. We will see later on. So how can we divide these ceramics? Ceramics is a very broad field, and so we usually have different ways of dividing the ceramics into different types. On the one hand, we have this general classification where we have traditional ceramics like silica and clay, pottery. So these are bricks, whiteware, tiles, pottery. This is all traditional ceramics. We are more working on the advanced ceramics. So usually these materials or the powders, therefore, are synthesized in a lab or from an industry, and they have very superior advantages compared to other materials we will see in a second. And they are produced rather in small quantities, but this is where we really get this strong properties of ceramics. To compare, usually you have on the one hand let's say a coffee cup which breaks when you let it fall. On the other hand, these advanced ceramics, they are even stronger than steel. So this is one type of classification. Another one is you can divide them according to the materials. On the one hand, you have these oxides, so alumina, zirconia, silica, magnesia. They as a metal with an oxide, and this is then the ceramic. Or a more difficult material to work with, or more difficult materials to work with are carbides and nitrides, because they have to be sintered in a special atmosphere, so they cannot be sintered under air. And yeah, as it's already said in the name, this is like a nitride or a carbide, silicon nitride, silicon carbide, aluminum nitride. So these are all examples for non-oxide ceramic materials. And another different way of classifying ceramics is you can use them as structural ceramics. So they are you use them for machine components, for electronic components. So they have really a structural fit. And the other way is to use them as functional ceramics. So they will have then optical or chemical functions. The most well-known one is piezo ceramics. So here you see the piezo effect on the right-hand side. This is an electrical effect which you know maybe from the lighter. When you push the lighter, you get out a spark, and this is where pressure leads to tension. And these are also ceramic materials. So it's really a broad range of materials, and we are trying to focus as well on the structural ceramics, but also we have done something with functional ceramics as well. And I will show you in a minute what kind of part of materials we are working on. But why are ceramics used, or where are ceramics used? Why do they matter? First of all, they are used when it's really about very high temperatures, where you need a good resistance to heat, or as well to abrasion, or if you need a very high hardness. So when you have a high wear thing. Then additionally, you could use ceramics where there's a high mechanical and dimensional stability necessary. This is usually for space applications or for optical applications. The good thing is with ceramics, they keep their mechanical strength even at very high temperatures, and also the corrosion and the oxidation resistance are very good also in in high temperatures. And this is also important. Ceramics can have, or in most cases, they are electrical and thermal isolating. There are also ceramics which are electrical conductive, but most ceramics are electrical and thermal isolating materials. So basically, to sum it up, ceramics are used in very harsh environments and are used where other materials fail. So, and for us, who are working a lot with ceramics, it's sometimes difficult to say that, but basically ceramics is in most cases not the first choice of the engineer. But when you need ceramic materials, you have seldom other choices to use. And this is again in these very harsh environments. And I was pointing out that I also will speak about the medical applications. And again, I think it's important to know that in the nature, basically also all materials are more or less in an oxidated status, and therefore it's easier for the body to adapt to the ceramic materials. And that's why they're working so good in biological applications or in medical applications. And we see clearly a trend, especially in the dental industry, a movement away from metal towards ceramics, because they are bio-inert, they have a non-allergenic reaction, so they are non-allergenic. They have a very low thermal conductivity, which is very good for implants, especially in the skull area. So such a cranial implant. Can you see my pointer here on the video? Doesn't matter if you're not. So on the right-hand picture, you see a cranial implant just on the very right side. And this can be also made of metal, but these people, they have then problems in the sunlight, or when they're taking a hot shower, that they feel the heat. And also, what's also a big advantage of ceramics is that you get no artifacts on computer tomography and MRIs. So once people have it in metal, they cannot do an MRI on this part again, but with ceramics you can do it. As well, you can easily sterilize them, and you can also have, they can have a very high mechanical strength and also a very good wear resistance. This is, for example, very important for hip cups. So this is one issue of ceramics, but what we are also doing and what our customers are also doing, they are using it also as a bioresorbable ceramic. So our body or our bones are a composite of ceramics and of collagen. And there are some ceramics which are resorbed by the human body, which can be resorbed by the human body, which is especially tricalcium phosphate. I will come to that a little bit later. So these are more or less the reasons why ceramics are used. You see basically alone from these things where it can be used, what are the effects of these ceramics. So let me come now to our portfolio. What do we have? And if you look here, you see all these things which I have already shown later. So basically, which means that the process allows us to use every kind of ceramic. So we can use here porcelain as one of these whiteware stuff, but also alumina, zirconia as the most common materials used. Also silica-based materials for casting cores. Then the nitrides, so we can also do silicon nitrides, so non-oxide ceramics, refractory materials, magnesia cordirite, but also piezo ceramics, so functional ceramics is what we also do. And as well, we can also have these bioresorbable ceramics, tricalcium phosphate, bioglass, hydroxyapatite. And one like exotic material we also have been working with is regolite, which is actually moon dust. So this was a project with the European Space Agency where we processed moon dust for them. I have to add it was a simulant. It was not really moon dust from the moon, but it has the same structure. And the idea is here to give the astronauts the opportunity to print parts up on the moon with using the resources from the moon. So these are just some materials we are using. As I said, we can basically use any ceramic material here. We do have a lot of research projects going on with other materials as well, like silicon nitride or other ceramics. So come to the next slide. Here for those, as I see, we have also some people who are aware of or who have knowledge in ceramics, and they would see that if they look at these material properties, that they are really comparable to conventional ceramic properties. But for those who have not so good, no education, no ceramic backgrounds, I mean, what you see here is that basically we can achieve the normal densities, very high densities, over 99%. We can, I think one of the aspects of this technology is that we can also achieve very low surface roughnesses or very good surface roughnesses. And the strength, as it's pointed out here, they are very, very good as well. And here with different powder composition. And so that you also believe me that they are similar to conventional materials. We have here just a very short comparison of an LCM processed part and an isopress part. And as you can see here, the material properties are more or less the same. So basically what you see that there is no difference between those materials. And I also want to stress one other material, which is alumina. This is a polycrystalline material and not like glass where it can see through. But if you treat it very well, you can get it translucent and you can read, as you can see here, you can read through that. And this is actually a proof that we can build without any problems. Because, if something is translucent, you cannot hide anything. You cannot hide cracks, you cannot hide voids or pores. And you really have to do everything correctly, starting from the powders up to doing the sintering. So if you want to check with one, let's say, process or additive manufacturing process to see if they really can process ceramics, you just ask, can you show me a translucent alumina? and if not, you just know that they are not working on the edge of ceramic processing. And how does the technology really work? So how do we come to these parts? I would assume that most of you have an additive manufacturing background and they have a good understanding. So I don't want to go into any details here, but show you a little bit how this technology is working. So the name of our technology is LCM technology, which stands for lithography-based ceramic manufacturing. And lithography means we are using light as a structuring method. I will show you in a minute. The big difference between most other 3D printing processes is that we have here a two-stage process. So as with every ceramic, with every AM process, we start with a CAD design and then we print the part. But in ceramic processing, we have then just achieved a so-called green part. So this is just a composite of the binder and the ceramic particles, and then they have to undergo a heat treatment. So basically, we have to bake them to achieve the final density. This means we have to debind the binder. We have to burn off the binder and then sinter the ceramic to full density, and then only then we have these ceramic properties, and then we have the final product. So, but how does it work? I think most of you are familiar with a DLP process. So basically, we are using DLP, but we are exposing from underneath. So we have a transparent vat where the light hits the material. The material gets solidified. It's a photosensitive resin with the ceramic particles filled in, and then we are pulling the parts out. If you want, I mean, there are a lot of videos available. I don't want to go into any details how the technology really works. We can answer them as well in the Q&A session if you really are deeply interested about it. But this setup, I think, is a very good approach on the one hand to achieve very accurate parts, because we can really control the layer thickness, and on the other hand, and this is, I think, especially true for ceramic materials, is that it's industrial ready. So we can we need very little material to work with and to start with, and we do not have to have the full vat with resin, because what's the problem with ceramics? On the long term, you have some settlement issues with particles, and if you have a big vat and you have settling issues, that's really a big problem then for the ceramic processing. But by doing this approach, we can very good have a very good this settlement issue under control, and we have very little material we have to keep as an inventory. And then after we have built up the green part, this material needs to be debind and sinter, and here you see the 3 steps. So after fabrication, we have the ceramic particles and the binder. First of all, we have to burn off the binder. Then we already see a little shrinkage, and then we densify to full density, and then we have a shrinkage. But this shrinkage is very predictable and homogeneous, and we can easily calculate it. So here you just see our machines which we have. So we have the Serafab system, the Serafab 7500, which was the first generation. Here we have the Serafab systems with different building envelopes. I don't want to go into details, but they are more for industrial use. And you can also have them modular in terms of having more system in one production unit. I don't want to go into any details here. I think that's not so interesting for this part. But let us speak now about applications and industry we are talking about. So what are these applications? We see, as you have already seen, some of these applications. We have 3 different areas I think, which we can talk about. We have these industry applications where we use mainly structural materials, but also some functional materials. Then we have the medical applications where we have dental and then non-resorbable and resorbable implants, and also medical devices. Last but not least, also a very big topic for us is aerospace, where they're used for casting cores, which I will show you in a second. And space and defense is, of course, a big topic there, and also propulsion for satellites and rockets. Uwe will go then in a little bit more in the industrial applications. I will just show you some applications here, which we see in medical and dental. We are already very well established in the medical field. So there has already been 10 surgeries performed in 2017, so already 3 years ago. And all patients are still feeling very well and are happy with their implants. This was a class 3 implant, so it was in the craniomaxillofacial area, so in the facial area. Our customers did a CE certification. So for this class 3, we already have an FDA approval. One of our more customers have an FDA approval in the US about medical devices, but currently just for 2A. We have also customers working in South America on these implants. We see that this is a very good application and a growing market. As I said, there is a clear trend, at least in dental, from ceramics, from metals to ceramics. And as well, if you just, to get a little bit into dental applications, so this is already there. Ceramics is very well established in dental, and we see for ceramics a good advantage, especially with ultra thin veneers or with dental implants out of silicon nitride or of other materials. So there are a couple of applications where we see that conventional forming is not performing very well for these applications, and where there's a technology gap, and additive manufacturing could fit in here very well. So one other application which is very interesting is ceramic casting cores. So basically they are used in the hot zone of the turbine engines. So basically the blades itself, they need a cooling because the temperature in the hot zone are actually higher than the melting point of the metal, and so they need to be cooled. And to have this, to get in these cooling channels, you need casting cores to keep that space free, so to say, and to leave the cooling channels behind that. And we see that this turbine engine manufacturers, that they are already working on the next generation of casting cores to even increase the temperature in the hot zone even higher. And there we already see that additive manufacturing could be a tool to manufacture these cores, because they cannot be injection molded anymore. So this is a clear trend here that more or less all turbine manufacturers are working on this technology to make the next generation of cores. But also, this is also very important to reduce the lead time for prototyping. So prototyping means 100 to 200 casting cores, to test them and to see how this is working. And this saves, as you can imagine, a lot of costs. And we get really a very good and reproducible accuracy there. And also the material properties are sufficient. And we have already seen some turbines casted, but not yet flying. But as you can imagine, it takes some time for all the certification here in this field to get the approval for really flying. last but not least, from let's say a space application, is something where the Adam Savage from Mythbuster wanted to print the Iron Man suit, and as you can see here, it was printed more or less fully in metal, but the arc reactor in the middle, which is the most important thing for Iron Man, this was printed out of ceramics. And you see sometimes, as I've pointed out in the beginning, ceramics are used where other materials fail, and they are used then where other materials cannot support it. And here is the same. So the arc reactor was built in ceramics, and the most important part of the Iron Man suit. So I would like to hand over now to Uwe. He will give you also some inputs from the industrial point of view. So Uwe.
Hello to everybody, also from my side. I want to show you some chemical applications and other applications which we are working on at Fraunhofer IKTS. We are using the technology from Lithoz to face different challenges. For example, in this case, the idea was to mix two fluids and to realize a temperature control inside the chemical reactor. First step was to generate an idea for this reactor that you can see on the right side. Here we have three different fluidic systems which are interwoven. Two of them are connected to allow the mixing of two fluids, and the third one, it's the green one, is used for temperature control. Then we need a method to design such a component to generate the mixer design. In this case, we use so-called gyroids. These are special mathematic structures. And then in the end, we had to introduce this into a complete component, as you can see here in the red one. And the technology of Lithoz allows us to realize such components by additive manufacturing. And here you see the final component. The outer diameter of the inner cylinder is about 12 millimeter in the center state. And here on the left, you see some pictures from our computer tomograph, which shows that also the small holes in the walls between the different fluidic systems are open, and we could realize a very nice resolution inside the component. Another idea was to use the technology to realize very complex ceramic substrates, for example, for a heater element. The idea was to realize a heater for a fluid which runs through. At first, such design was generated, and then the idea was to use other technologies for functionalization of this component. We use aerosol printing technology to bring a heater structure on the outer surface of the component. And here you see the final component. The heater structure or the substrate was realized in alumina, and after sintering we use aerosol printing to realize this heater structure based on ruthenium oxide in a glass matrix. And here in this picture on the right side, you see that it can be used to heat up the whole component. And because of the complex structure inside, it's possible to transfer the heat from the outer surface to the fluid which runs through. And now, a third example, what's possible with this technology, we also generate a ceramic chain, which can be used for transport applications under environment. And the technology of Lithoz allows us to realize alumina chain, which is movable even in the sintered state. So that three different examples for applications which we are working on at IKTS using the technology of Lithoz. And then I will hand over to Johannes.
Yeah, thank you, Uwe, for giving us also an insight about some applications in this field. Let me now try to summarize a little bit, and then I've seen there are a lot of questions, so I will keep it rather short to answer then also the questions you have. But basically, what we have seen, I mean, what is already now state of the art is that the 3D printing processes works for different kind of ceramics. Sorry. So from oxides to nitrides and carbides, from grains, different grain sizes and everything, that basically, yeah, there is not really a limit. Very well is ceramic used where other materials fail. I think this is one of the things that you should keep in mind when you're using ceramics. You know, you could have a huge benefit when it comes to wear resistance, heat resistance, and stuff like this. And we from Lithoz, but also IKTS, is also trying to support your needs with know-how and our experience. So even if you have no ceramic background, you can get started with this technology. We have a lot of installed machine base out there. There's a lot of customers which are willing to produce for you, or which are willing to develop with you. Maybe some like IKTS, they can develop with you certain applications and support you with your needs. Additionally, I would also like to invite you for the AM Ceramics, which is today or this year a virtual conference. So it is our fourth conference in this field. So and we wanted it this year to do it together with the IKTS in Dresden. Therefore, you see also the Frauenkirche in Dresden, very well printed with our technology. But due to Corona, we have to switch to a webinar, and it's free to attend. So for those who really want to go deeper into ceramic 3D printing, there will be a 2-day event focusing on additive ceramics. So it's more the AM ceramics, but also on other ceramic technology on these 2 days. So you are very much invited to join here our conference. So we've come up to an end. I'm happy to see so many questions, and as Carlotta was already saying, if some questions have not been answered during this time, we will definitely reach out to you and answer all the questions you have. So Carlotta, I will, and if you have additional questions, feel also free to send us emails and ask whatever you want. So Carlotta, I think I will pass over to you, and you will moderate now the Q&A session. So thank you very much, everybody, for your attention, and looking forward to a vivid discussion.
Thank you, Johannes and Uwe, for this interesting presentation. It's true that we received a lot of questions. So I think before we go into the technical ones, because you were talking about the predictions and your outlook on the ceramic 3D printing sector, so we had a question asking, actually, I would like I would like to ask all presenters about their predictions on serial production for ceramic parts by additive manufacturing methods in the years to come.
Mm-hmm. Yeah, I think I can comment on that. So we already see serial production. So on the one hand, we have customers who are working on mass customization applications. So like in dental or in implants, you know, every part is customized, and they are printing on it. And here we are talking about, in the meantime, between 30 to 50,000 parts per year, different for each part is different there. But we also see serial application at our customers, especially in the medical device industry. And there we have about serial production in the range of 10,000 parts upwards per year, so between 5 to 20,000 parts per year, which are produced by additive manufacturing. So yes, we are already in serial production with ceramic processing, and
Okay, great. And actually more technical questions, because we had a lot of those, especially when you were talking about debinding. We had a few. So I'll start with one. Debinding will leave voids where the resin was. How do you then achieve nearly 100% density without grain growth?
Or maybe Uwe, you can comment on that.
Uwe, you need to put your mic on. We can hear
you.
Sorry,
I lost the connection. Please repeat the last question.
Sorry. So the last question was, debinding will leave voids where the resin was. How do you then achieve nearly 100% density without grain growth?
Yeah, a little bit grain.
Okay, Uwe, your connection. Uwe, sorry, Uwe, your connection is not good, so I'm gonna turn off your mic. Actually.
Yeah. Okay. So I will answer the question. Yeah. Basically, what we see when it's perfectly right. So when the binder is burned off, you have voids, and then during sintering, the particles are moving together, and then we see shrinkage, and this is the normal way how ceramic are processed. So every ceramic processing has this issue with shrinkage. So you have about 50 to 60 volume% ceramic particles in there, and then you have the shrinkage where they come closer together, and then if you do it correctly, you don't have a huge grain growth. So that's normal ceramic processing, and and shrinkage is of course then the key to get rid of the voids.
Okay, and is debinding done only thermally, or there are other strategies to remove the binder?
Yeah, I mean, basically there are other strategies, but with our technology, we just use thermal processing to remove the binder.
Okay, and someone asked, what is the residual percentage of binder after debinding? This is quite specific.
It's the whole binder is totally burned off, so there is no residue left. And this is, for example, what you see with transparent alumina. If there would be carbon residue in there, you would not get it transparent.
Okay, and someone was actually comparing with Peck and Peck. So in which cases would ceramic be preferred to these materials, as they have similar advantages in terms of heat resistance, conductivity, chemical resistance, etc., and are both used in similar industries such as aerospace and medical applications?
Yeah, I mean, Peck is definitely an interesting material for these kinds of applications, but it's a very difficult material to be shaped, and hence in some cases ceramics are the better choice. It's if you talk about medical devices, You're right that Peck is used, but my feeling is that that also there is a shift away from plastic materials in your body towards ceramics. And I'm not the medical expert in this field who can really tell you what's the clear difference. But in most cases, what we see, especially when it comes to skull, the doctors and the hospitals, they would rather use ceramics than Peck.
Okay. And then we had a few questions also on the technology itself, asking for what is the resolution like, and also what limits the build size of parts. So how...
Yeah. So the build size of parts is limited more or less by the wall thickness. So the technology is not perfectly suited for big parts because they tend to have big wall thicknesses, and then it's difficult to debind them. So to get all the binder out, that's difficult. So and I think basically there are better technologies suited for big and large parts. You will see much more to come, maybe late this year or beginning of next year. And I think even all lithography-based approaches are not good for the big parts. And the first question was?
It was actually about Lithoz technology. Yeah, the resolution on your technology.
Yeah, there are different resolutions available, so from 25 microns to 75 microns. But it depends mainly on your application, which resolution you would need. This is not the limiting factor. We have seen that most of our application, or the surface roughnesses I will show you, were all printed, for example, with 40 micron resolutions.
Okay, and okay, given all these considerations, can someone start ceramic 3D printing without much know-how? What's the process like to integrate the technology?
So we already have a couple of customers which had no ceramic background, so which were starting up with a completely new application, or just wanted to enter into the additive manufacturing field of ceramics. And it was a little bit more difficult, or not, it was more difficult for them in the beginning, but they really, they were managing to cope with the ceramics very, very fast. So they had maybe a longer learning curve, but they achieved also very, very good results with the ceramic 3D printing.
Great. And in the medical field, we know that quality assurance is a must. So how are you addressing this topic?
Yeah, quality assurance is a very, very important task. And we are working here very strongly with our customers, but also internally, to be sure that the quality is right, and that we can deliver the quality needed for medical applications, but also for aerospace applications. So we have currently ISO 9001 certification, but we'll go for 13485, which is the medical certification. But as I said, certification is not enough. You really need to build up your quality assurance system, not only a management system, but also assurance system. And we have been, as I said, so successful that our customers are already in human use since 2017.
Great. And during the presentation, you showed a translucent part made from alumina. And what prevented you from obtaining a completely and fully transparent ceramic?
Uwe, can you comment on this, or is your connection good enough so that I don't speak all the time?
Currently not. So I can try it. So.
Oh, sorry, I think the connection is not good enough. So I have to cope with all questions. No, but it's okay. What was the question now again? Like the translucency?
of the alumina, what actually prevented you from obtaining a fully transparent ceramic?
We have alumina alone cannot be made fully translucent because due to the optical structures and to the grain sizes, this is not possible to have a really transparent look like from the glass window. But there are other ceramics which can have really a glass-like translucency or transparency, but we have not yet worked on them. They are used for armors and stuff like this, but basically I don't see an issue to make this happen. I mean, it's work to be developed, but we have not yet the request to do so.
And actually, what's the minimal grain size in alumina? If someone asks.
The minimal grains to get it transparent, you mean? So the grains we are usually having are in the range of a couple of between around 100 nanometers is the starting grain size. But basically, we can use all grain sizes, so from a couple of tens of nanometers up to hundreds of micrometers. So that's really a broad range, but of course you need to have a dedicated powder to be able to get a translucent or transparent ceramic.
Okay, and actually a bit less technical. So what is your experience or customers' experience with serial production? You've touched a little bit on this, but if you could expand.
Yeah, I was very excited to see how fast our customers are moving into serial production. One issue was it was in the very beginning, maybe it was our second or third printer we installed. And after a year or so, I was talking to our customer and he was saying, yeah, we are using now 3 shifts. I said, how can you use 3 shifts? We're training 2 people. I said, well, it's not a big deal. We have our technicians all time there that just tell them what to do. And the people from the workshop, they just load the job and start the next print. So we see actually that it's easier for ceramicists to adapt additive manufacturing in serial production than it was for metal people to adapt the metal AM. So it's actually very fast. Within 1 or 2 years, most of our industrial partners have switched to serial production with a couple of thousand parts.
Okay, and you mentioned metal, and a few people were asking if you, first of all, can mix the ceramics and metal in this process, and can you just print with metal in a similar process or not?
Yeah. Basically, our philosophy is always that we are adapting the technology to the powder and not vice versa. So when we're starting to work, we were also starting to work with metals. And we have seen that you need a different kind of process to make it perfectly happen, and this led then to the to a spin out already of Lithoz. So we founded Incus, and they having the same very similar process as we are using, so lithography based approach, but for metals, and this is also working very well. We see as well very high surface quality and a very good tolerance and reproducibility. So if you want to check it out, you can find it on the internet. It's incus3d.com. But as well, we can combine also the ceramic and metals in one process, as Uwe was pointing out. You could spray afterwards the metal material on the ceramic, or we are also working with a multi-material machine where you can use 2 different materials and where you can mix ceramic and metals and build up a 2-component or hybrid part.
Cool. So we are approaching 5 p.m. So I will ask one last question, and then again, if there's any questions that we haven't covered, you can contact Lithoz directly, and also there will be a replay of this webinar. So the last question was about printing parts. Is it possible to ask you to print the parts, or is it a question of always integrating the technology and investing in in-house equipment to create these parts?
Yeah, basically, we as Lithoz, we do not print parts as a service. So we are developing applications. Yes, we are supporting our customers in developing application, but printing service is usually done by our customers, as for example, IKTS. So if you have a specific part to be printed, you can contact Uwe or any other of our customers. We have a list of them, and they would be happy to provide this service for you.
Okay, great. I think this concludes and wraps up this webinar. I just want to ask you if you have any last comments before I finally wrap it up, but we are almost done.
Yeah, maybe I just want to add, so really, if I see that there are a lot of questions unanswered, we will try our best to answer them very quickly, but since there are really a lot, it will take some time. So don't be sad if it takes some days, but be sure that maybe by next week, so by the end of next week, you should have received an answer to your question. Sorry. But thank you so much for participating in this vivid discussion, and thank you, Carlotta, for moderating it, and also thanks to you, Uwe, for supporting us here. But unfortunately, the connection was really bad, so you left all the talking to me. But thank you so much. And as I said, if you have any further questions, feel also free to get in contact with us directly.
And also thank you from my side, and I will support Johannes during answering the questions.
Okay, great. Thank you to you both. I think the number of questions just show that people are definitely very interested and want to learn a lot more. So it's always a good sign, and Lithoz and Uwe will come back to you on your questions. So in the meantime, have a great day, and thank you for attending. Thank you both. Thank you.
Bye-bye.
Bye-bye, everyone.
Bye.